What is bonding? Bonding is a network technology that combines multiple physical connections into a single logical interface. This allows multiple connections to act as one, providing higher bandwidth, redundancy, and better performance. It is commonly used in networking to optimize resource utilization and ensure uninterrupted connectivity. Increased bandwidth combines the bandwidth of multiple links for faster data transfer, ideal for high-demand applications. Redundancy and failover ensures network uptime by rerouting traffic through other connections if one fails. Load balancing distributes network traffic across multiple links for optimal usage and reduced congestion. Improved performance lowers latency and enhances throughput for applications that require consistent and reliable connectivity. Scalability easily add more links to meet growing network demands without overhauling existing infrastructure. Cost-effectiveness utilize multiple affordable connections instead of relying on a single expensive high-speed link. Balance RR, round robin. Description, sends packets sequentially across all links. Use case, high throughput for non-ordered data. Example, trucks take turns carrying boxes, one by one. Active backup. Description, one link is active, and the others stay idle as backup. Use case, high reliability. Switches to backup if the main link fails. Example, a spare tire kicks in when a flat happens. Balance XOR. Description, chooses a link based on a hashing algorithm, e.g. MAC/IP. Use case, for load balancing with minimal packet reordering. Example, packages are sorted by labels, to specific trucks. Broadcast. Description, sends all packets on all links simultaneously. Use case, highly reliable, for critical data. Example, a megaphone announces the same message to all. 802.3 add, LACP. Description, uses the link aggregation control protocol for dynamic link bundling. Use case, when the switch supports LACP. Example, teaming up trucks dynamically based on available capacity. Balance TLB, transmit load balancing. Description, adjusts traffic load based on the current link speed and capacity. Use case, for environments with uneven link speeds. Example, faster trucks get more packages, slower ones get fewer. Balance ALB, adaptive load balancing. Description, balances both sending and receiving traffic dynamically. Use case, for environments needing adaptive traffic distribution. Transmit hash policy. In Mikrotik, transmit hash policy, THP, is a setting used in bonding to decide how packets are distributed across multiple physical links in a bonded connection. When using transmit hash policy equals layer 2 and 3, the bonded interface uses information from both layer 2, like MAC addresses, and layer 3, like IP addresses, to determine which link a specific packet will take. This approach ensures better distribution and efficiency. When combining multiple cables into one virtual connection, bonding, Mikrotik needs to decide how to send data across those cables. Transmit hash policy is like a sorting rule. It decides which cable each piece of data should use. It looks at the sender's MAC address, device ID, and IP address, internet location. This helps spread the load across all cables, avoiding overloading one while others sit idle. Example, think of trucks carrying goods. This policy decides which truck gets which package based on labels, MAC and IP addresses. MIA, Media Independent Interface. What it does, checks if the physical link is up and working. Works at the hardware level to monitor cable or interface connectivity. How it works in bonding, ensures that a bonded link is still active. If a link fails, bonding will stop using it. ARP, Address Resolution Protocol. What it does, verifies the network connectivity by sending ARP requests to a specific IP address. Confirms that the other side of the link is reachable. How it works in bonding, sends small test messages, ARP requests, to ensure the network is functioning, even if the cable looks fine physically. Useful for detecting upstream failures. In our office setup, the main router has all ports capable of 1 gigabit per second, while a second Mikrotik router is being used as a switch for office workers. However, this second router has limited port speeds, with most ports supporting only 100 megabits per second, except for Ether 5, which supports 1 gigabit per second. As an IT professional, instead of immediately purchasing a higher capacity router, you can optimize the setup by using port bonding. This allows you to combine multiple 1 gigabit per second or SFP ports to effectively increase throughput and distribute the load. This method can be applied not only in this scenario, but also across the core network to enhance speed and efficiency without additional hardware costs. If one link within the bonded group fails, the traffic will seamlessly fail over to the remaining active links, ensuring uninterrupted connectivity and improved network resilience. On the office router, our upstream connection is on Ether 2, which has a gigabit port and a 200 megabits per second line. To achieve speeds greater than 100 megabits per second, we can bond Ether 2 and Ether 3 together. I will use Balance RR mode with MII link monitoring and Layer 2 for the bonding setup. We'll assign an IP address to serve as the LAN gateway for the office devices, and the bonded interface will be used for this connection. We'll configure the DHCP server next. Don't forget to set up a firewall NAT rule to perform source NAT for all traffic. This shows that Ether 2 is running at 1 gigabit per second, while Ether 3 and Ether 4 are running at 100 megabits per second. Let's log into the switch router to verify that Ether 2 and Ether 3 are running at 100 megabits per second, and Ether 5 is on a 1 gigabit per second port. Let's configure the bond by adding Ether 3 and Ether 4 as slaves, while still using Layer 2 and MII link monitoring. Now we can see that the bonding is active and running. Let's run the DHCP client on the bonded interface and check if we receive an IP from the office router through the office's bonded interface. Great, we've received an IP. Now, we can create a bridge, add the bonded interface, and include Ether 5 so that my PC can also obtain an IP through the bonded interface. Let's disable and then re-enable the network card on my PC to prompt it to request an IP address from the DHCP server. After that, we'll check if my PC can access the internet. Everything looks good, and I now have internet access. If you see that you're receiving the correct IP but your PC isn't getting internet access, try unchecking the hardware offloading option. Disabling hardware offloading on your Mikrotik router forces the router to process traffic with the CPU instead of the switch chip. Some Mikrotik devices or switch chips don't fully support advanced configurations like bonding or NAT with hardware offloading enabled. Disabling it can resolve issues like DHCP failures or lack of internet access, ensuring smoother traffic processing. Let's disable Ether 3 to run at only 100 megabits per second for testing. Let's enable Ether 3 and run a speed test to see the results. Great, we're getting more speed through the bond now. Let's add another interface to the bond to reach up to 300 Mbps and run the test. It looks like it's working well now. Let's check the bandwidth between the switch and the main office router to see how well the bonding load balances. As I mentioned, if an Ethernet connection fails, you'll still be online, but the speed will be limited until the Ethernet connection is restored.